first period, and she told me there was no sound. So I doubt too many of you are going to rewatch that one 5 times. But I got to fix it today. All right, so limits at infinity to me are so cool, and they are going to be a huge, huge, huge part of what calculus is based on. So the idea that you're going to see with calculus is you'll often be looking at, as I get closer and closer and closer to this. Let me give you just like a quick, really quick idea, because a lot of times students want to see just a glimpse of like what calculus is. So like we know how to find the area of this rectangle really easily, right? Just length times width. That's really easy. But if I want to try to find the area of this shape, the area underneath the curve, not so easy, right? So one of the big questions that's asked in calculus is, how do I find the area under this curve? Which actually has a lot of implications for like physics and all kinds of applications that you can apply it to. But so since I can't find the area under the curve, one thing I could do is I could just make like a bunch of little rectangles like this. I could put like the end point here on the graph and make kind of like a bar graph. I could make a bunch of different little rectangles. This is what you would call a Riemann sum. You don't know that or need to know much about it yet. But if I found the area of all of those rectangles, because I could find the y coordinate of that point. I could find the height of this if I know the equation for that line right there. So I could find the area of all of these rectangles and add them together, and it's going to be kind of close, right? You can see I've got like blank space here, but then I got like the overhang here, so maybe they might kind of cancel each other out a little bit. Looks like it's going to be a little bit too much overhang to make up for what's here. But it's not going to be exactly right, but it's going to be closer, right? So I could find the area of all those rectangles, add them together, I get an estimate. What would make that estimate better? What's something I could do to make that estimate better? Still using rectangles. I could, that is a good place to go, is like if I kind of add like a triangle here, which actually makes it the trapezoidal rule instead, because these are technically trapezoids if you have a shape like that. But is that what you're talking about? Yeah, if we add that in, that is something we do in calculus that would make it better. Okay, so we could use trapezoids. That would be better. What else could I do that would make this better? What about more rectangles or more trapezoids? What about, instead of doing it like I've done here, what if I do, what if I do teeny rectangles? I'm not going to draw them all in. It'll take forever. What if I make them tiny? There'll still be a gap, but is the gap as big? It's smaller. So if I have little bitty rectangles, my estimate would be better. Right? So up here I had 1, 2, 3, 4, 5, 6, 7, 8 rectangles. Down here I might have 50 rectangles. What would be better than 50 rectangles? 100. What would be better than 100? 7,000. What would be better than 7,000? 7,001, right? So if I took these rectangles and did the limit as my number of rectangles approaches infinity, I would actually get a perfect area underneath the curve. So you don't need to understand that. That's just like an idea of where we're going. That's the base, that's why limits in approaches infinity are like the basis of calculus. I promise if you take calculus, I will explain that in much more detail, and we'll talk about it much more. So if you think it sounds crazy and you don't understand it, that's okay. But limits at infinity are really important. I know Jack Zamudio told me that it's one of the main things that they looked at in Calc 2 also. He used that a lot, so it follows throughout, because it really is like the basis of what calculus is made of there. So it's really important. We are just doing sort of a basic introduction to limits and infinity. We could go way further with it, and we'll go further with it if you take calculus. But we're going to do sort of a basic introduction here. So let's look at some graphs first, because we looked at the tables at the beginning. I would like to now look at some graphs to kind of put that together, and then we're going to go to what the algebraic part of it looks like. So if I look at this graph here, and I'm asked for the limit as x approaches infinity. Okay, so I can't see where x equals infinity because it never actually gets there, but positive infinity is over here on this side, right? What does it look like is happening on this graph as we, looks like I got a horizontal asymptote right there. And we're going to make that assumption that we have a horizontal asymptote right there. So, remember, whenever I report the answer to a limit problem, I need to give the y value. What y value do we approach as we go this way? 1. Okay. The limit as x approaches negative infinity would be on the left side of the graph, right? So on the left side of the graph, what value are we approaching? Also approaching 1. Lots of times when you have horizontal asymptotes, it's the same on both sides. Infinity and negative infinity, you get the same thing. But not always. Because if we look at the, oh wait, I've got more. Hold on. We'll look at a not always scenario here in a second. For example 3, I've got the limit as x approaches 0 from the left. So, limit as x approaches 0, which is right here, from the left. 0 from the left. What do I go to? That goes up, 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 up. That's a vertical asymptote there. So you would get positive infinity. And then the limit as x approaches 0 from the right. So 0 is right here. As I approach 0 from the right, where do I go? Negative infinity. And especially for today, it is technically okay to say does not exist for those last 2 answers, but I want us to use the positive or negative infinity for that. I want us to give the most specific answer, which is that positive or negative infinity. Now, 1 and 2, this is what we're going to be focusing on mostly today. These are limits at infinity. And that is where x approaches positive or negative infinity. So what we're going to be mostly focusing on today are those limits at the ends of the graph. As far right as you can go, as far left as you can go. That's what we're looking at today. These right here are called infinites. Limits. And these, the answer equals positive or negative infinity. These are not limits at infinity because x is not approaching infinity or negative infinity, but they are infinite limits because the answer is positive or negative. We will see some where we're looking at limits at, and you can have both here. You can have x approaching infinity and the answer also being positive or negative infinity. So you can have both. We'll see some of that as well. All right, let's look at this second graph here. So for our second graph, we've called that equation there g of x, and I want to know the limit as x approaches infinity of g of x. So Lily, if we look at that graph, what would our limit as x approaches infinity, which would be over here on that right-hand side, be? All right, so as we follow our graph over to this edge, is it leveling out? Or is it looks like it's leveling out. What is the y value that it looks like it's leveling out at? It's going to be 8, right? So our limit as x approaches infinity would be 8 for this one. Okay, so Sophie, what about the limit as x approaches negative infinity? That would be over here on the left side of the graph. It looks like it is 2. There. So we level out, and we're going to give that y value where we level out. Just like with other limits that we've done, your answer is your y value. Make sure you're always pulling that answer from the y-axis, not from the x-axis. So you may see a few of these mixed in with some of the graph problems that you're going to see. When I may ask for some limits as x approaches infinity or negative infinity, just know infinity is the far right side of the graph. Negative infinity is the far left side of the graph, and you're looking to see if it levels out at anything. But mostly today we're going to be looking at the algebraic form of this. So, all right, so we're going to do a couple of these where we're plugging in, sort of plugging in infinity. Okay, so I've got the limit as x approaches infinity of negative x to the 5th minus 7x to the 4th minus 7. So let's think about what's going to happen a little bit here, okay? Before I go straight to like the shortcut for you. So let's pick, I'm going to pick some numbers that are going to get larger. So like if I'm sort of making myself my own table, right? We could use the calculator, but I kind of want you to see the numbers plugged in to see what's happening. So if I plug in 1, right? I've got negative 1 to the 5th minus 7 times 1 to the 4th minus 7 here. And only the 1 is being raised to the 5th, so here you get negative 1. Here you get minus 7, minus 7. So we get negative 15 for that. Okay, let's plug in 10. Try to stick to numbers that are going to be fairly easy to do by hand, because I want you to kind of see what's happening here. So we got negative, we got 10 to the 5th minus 7 times 10 to the 4th minus 7. So we got negative, this will have 5 zeros. This will have 4 zeros. So we got negative 10,000 minus 70. Yeah, you're right. I didn't put enough zeros there. 100,000 minus 70,000 minus 7, so we get like negative 1,707. Okay, I'm going to do one more by hand just because I'm kind of wanting you to see what's happening here. And then I'll show you how to do this without having to do every one by hand. So now I've got 100 to the 5th minus 7 times 100 to the 4th minus 7. How many zeros does 100 to the 5th have? I think it's 10. Yeah. Check and make sure it's right. Because you got 2 zeros and 5 times will give you 10. So you got, I'll put some commas in here. There. Okay. How many zeros are you going to have for the 100 to the 4th? 8, 1, 2. And then you got that little -7 over there on the end. All right, so I've got, if I put that together, I got negative, oh yeah, need a negative right there. I got 10,700,000,007. All right, so let's think about it. Now, all of these were negative, but does that 7 really matter? Is it changing things much? No. Does this middle part matter? Kinda, but as your numbers get bigger and bigger and bigger, it matters less. Because I said I was only going to, let's just think about this next one. All right, 1,000. Why is it not writing? It's possessed. Okay. 7 times 1,000 to the 4th minus 7. So now I got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 zeros right there. Here, how many zeros am I going to have? I'm only going to have 12. All right, so, and then I got that 7. That poor little 7's not doing much, right? This matters, but it matters less than it did on the last number.
Because like the higher the number goes, like the farther apart the zeros will be.
Yes, because like here we had 10 zeros for this one, and we had 8 zeros here. Then this one we had 15 and 12. The next 0 that we add, they're going to be even further apart. So as x approaches infinity, which number is the only number that really matters? The one with the highest exponent. Because well, you can see really easily at the beginning here that 7 is not doing much. And all of these were negative values. I should have done one where some of them were negative and some of them were positive. But it's really just your variable with your highest exponent that at infinity is going to matter. Because it's going to be so much bigger than the other numbers that it doesn't matter. So, whenever we do problems like this, if you have one that is just a limit as x approaches infinity of an expression, you really only have to look at whatever has the highest exponent. Because that's the only one that's going to matter whenever you're looking at really, really, really large numbers. So if you look at it here, if you think about plugging that in, you're going to have negative infinity to the 5th power, and infinity to the 5th power is just infinity, so you would have negative infinity for that. You're going to approach negative infinity, which you could see from our table. This is an option for you on the table, like if you have trouble with this, you could always, even if it's on the calculator inactive, you could do a table by hand. It's just not, takes a while, right? But you could do a table by hand, plugging numbers in to see what happens. But no, you cannot make that assumption. For a reason else. Now on this problem, it would be, actually no. All right, so since we're what we're thinking about here is we're taking negative infinity, and you're thinking like you're plugging in negative infinity here. All right, sort of.
Since it's approaching infinity, you want to just plug
Yes.
it in.
Yeah. Yeah. It really wouldn't. Yeah, you're right. Because they're all negative, your exponents don't really even matter here because everything's going to be in negative anyway. But let's say that this was a positive 7, x to the 4th here. It's still going to be negative infinity, even if that is a positive, because at large numbers, the highest exponent is the only one that matters. because it's going to overpower anything else eventually, right? For small numbers, if I plug in 1, if that's positive, then I end up with a much higher number. Like it does matter. But for large numbers, x to the 5th is the only one that's going to matter. So really, you only have to look at your highest exponent. But because they're all negative here, you wouldn't even have to consider that. Now, for example 8, I'm looking at negative infinity. So I could think about like plugging in for all of these, but which one's the only one that matters for really large numbers? This x to the 5th, right? So this time you're plugging in negative infinity to the 5th power. When you raise something to the 5th power, does the negative stay or does it go? It stays. So I would have negative infinity here, and that would be my answer. What would the answer be if that right there was to the 4th power? It'd be positive, because when you raise something to an even power, it gets rid of that negative, because you're doing a negative times a negative times a negative times a negative, which is going to give you a positive. So whenever you see problems like these, where it's just straight plugging into a polynomial, you really only have to look at that highest exponent. So I spent a lot of time explaining that because I wanted you to see why, but when you see these problems, you should be able to do them really quickly, because you're just saying, oh, highest exponent is x to the 5th, plug in a negative infinities. These answers are going to be either positive infinity or negative infinity. You won't get another answer for these. Okay. All right. Let's consider the limit as x approaches infinity of 1 over x. Let's make us a table. This will be a little easier to make a table for. If I plug in 1, I get 1 over 1, which is 1. What about if I plug in 10? 1/10. What about if I plug in 100? 1 over 100. I need some lines right here. What about 100,000? 1 over 100,000. What is happening to that y value? It's t tiny right there. Like we're getting closer to 0. Think about it. This is like, say that we got a pizza, right? And x is our number of people. If I've got one person, I've got one pizza, I'm splitting between one person, that person gets a whole pizza, right? But if I got 10 people, everybody gets 1/10 of a pizza. That's not much. If I got 100 people, everybody gets 100th of a pizza. Is this worth showing up to the pizza party for? It is not, right? If I got 100,000 people and we're all sharing one pizza, everybody gets like a microscopic crumb of a pizza, right? It's not helpful. So the limit as x approaches infinity here is 0. Okay, let's say that we are having a pizza party and we order 1,000 pizzas. Okay, we got 1,000 pizzas. So if only one person shows up, how many pizzas does that one person get to eat? 1,000 pizzas. He's the only one that showed up to the party, but he gets to eat 1,000 pizzas.
That seems like kind of stuff could be awesome.
So, what about if we have 10 people? They each get 100 pizzas. So, you got 10 friends, each of you with 100 pizzas. You're going to have a good time, right? All right, if we have 1,000 people, how many pizzas does each person get? 1. Now you've really got a party. You've got 1,000 people. Everybody gets their own personal pizza here. We're talking full-size pizza. You got more. I mean, for most everybody, I feel like if you can eat more than one pizza in a sitting, their pizza is really thin. But Yeah, I could too. Thin crust is a different story. We're talking regular crust pizzas here. We're going to say if you eat more than an entire large regular crust pizza at a time, you're probably not making good dietary choices. All right. So, yeah, so we probably should not do that. So up into 1,000, we got a good situation here. But what's going to happen when we start having more than 1,000 people at our party?
You have to kick some out.
If I've got 10,000 people that show up to this party where we got 1,000 pizzas,
10 pieces per person.
now everybody only gets a tenth of a pizza again.
That's no bueno.
So you're getting like one small slice. You're feeling cheated about what's happening here. And then if I have 100,000 people, everybody's only getting a
What if we invite everyone
100
in the
pizza.
world to this said pizza party?
So then we've got like 8 billion,
Yeah.
right? So we got 1,000 divided by 8 billion, and
It's a few.
it's not going to be much at this pizza party here. Yeah. So even though we started off with 1,000 pizzas, which sounded like a lot, if we let that x go to infinity, what do we still get?
Small number.
We get a t tiny number, right? It still goes to 0, even though we had 1,000 pizzas. Now, obviously, if we're actually talking about pizzas and people, there's limitations on this. There's not infinite people in the world. We've only got like 8 billion, so we can't have more than that at our party. And, you know, there would be limits to the number of pizzas you could buy. There would be limits to how tiny of a piece of pizza that you could cut, right? You would be getting like splitting atoms at some point if you got too many people. So, but theoretically, if you had infinity people, it would eventually get closer and closer and closer and closer to 0, right? So does it matter what that top number is? There's no number of pizzas that you could have where you would have enough for infinity people. And you may want to answer you could have infinity pizzas. But in that case, if you had infinity pizzas, the top would be an X and not a...
Just be a 1. Right?
It would be 1 in that case. But the top would have to be an X. It wouldn't be a number. But as far as numbers go, even if you have a gazillion pizzas, a gazillion pizzas over infinity people is still going to be 0. All right. What's going to happen in this situation?
You have one pizza, they're all female and giving birth at the party. And that is how you find it. And that's true. What? What? No? True though. Look at it. If you invite 2 people and they both give birth at the party, that's 4 people now.
He may be correct.
That's 2 people in a baby.
This baby also is able to eat a slice of pizza here.
Yeah.
You're getting out there, Jeremy, but I see where you're going with this. So if you have, well, but if you have one person, 1 squared is 1. But if you have, I think it'd be 2x. I think it'd be 2x for the giving birth scenario. It'd be a 2x, not an x squared.
What about 0.5?
They'd have to have like an increasing number of children. I don't think we can go there. Let's not get too carried away with our pizza party birth scenario. So this would be 1/4, right? 3 would be 1 over 9. If we went to 10, skip to 10, we'd have 1 over 100. What happens here? Not enough pizza, 0. And it goes to 0 even faster, right? Because, like up here when we were doing 1 over x, at 10, we had 1/10. Here at 10, we got 1 over 100. So it's going to 0, and it's going to 0 even faster than it was before.
Yeah.
What about here?
Well, you got 50 pizzas, so.
We got 50 pizzas this time, but we're doing x to the fourth. So, like, if we start plugging in numbers, one person, 50 pizzas. But two, you'd have 50 over 2 to the fourth is 16. So that would be
25 over 8.
25 over 8. Let's get decimal just to 20, 25 over 8. 3.125. Sorry.
What's like 3? Oh my god.
It's possessed. Here we'd have 50 over 3 to the fourth is 81. Now we're down to less than a whole pizza. So 50 divided by 81. And then, like, if we had 10, now we're at like 50 over 1, 2, 3, 4 zeros. So nearly nothing here. 50 divided by 10. You get 0.005. So what does this one equal? All of these are 0, right? Okay, so what assumptions can we make?
Next to the bottom, then it's going to be 0.
Okay? All right, so if you have an x on the bottom, no matter the power, so I'm going to put x to the n. All right, what has to be on top?
Anything that's not a thing. Just a number.
A number, right? It needs to be a number, because if we didn't really consider what's going to happen if I have, like, x to the 7th on top, right? We didn't have any variables. So if I have a, I think I used different letters on the next, but if I have where b is a real number, and
If it's like negative,
oh, that's a good question. What about if I approach negative infinity? Obviously, my pizza application starts to fall apart.
you give Domino's.
But if I had negative here, what if I approached negative? I'd get negative. I'd have negative 1/10. Negative over. I'd have negatives of everything. What does my y value still approach? It's still getting closer to 0.
The other way around.
It's just you're coming from the negative side of things, right? So it still approaches 0, just from the negative side. In most cases, it'd actually still be positive with that square because it would square it. But so I don't think it matters whether or not. I think x can approach positive or negative infinity. It really doesn't matter. B has to be some real number. It doesn't really matter whether it's positive or negative either, because the bottom of this fraction just keeps getting bigger and bigger and bigger and bigger, right? There is one more condition we have to have. We got to have some restrictions on that exponent. If I have 1 over x to the negative 4th, then that, what do I do with negative exponents? I move it up to the top. That would actually be x to the 4th. So can I have negative exponents? No, because negative exponents would actually move the variable back up to the top and it would change what we would have. What about, what about like fractional exponents, like x to the 1/2? Are those okay? I think those will be okay, right? It's like the square root of x. It's going to go slower, but it's still going to be okay. So I think we just need to say that my exponent has to be greater than 0. Right? You have to have a positive exponent there. It could be anything. It could be 1 over 100. X on the bottom. Your exponent is positive, and your top is a number.
But what if your numerator is infinity, then it'd just be 1, right?
Infinity would not be considered a real number. So this would cover that scenario. Yeah. Okay, so I think I've summarized this probably with some different variables on the next slide. So our conclusion here is that the limit as x approaches positive or negative infinity, it doesn't matter, of a number, some sort of constant, a real number, over x to the r power is going to equal 0. So if the top of your fraction is a number, the bottom has a variable raised to a positive power, then for really, really, really big numbers, the bottom of that fraction gets really big and you approach 0. Okay? This is the key to everything that we are going to do. You may be getting worried and think that homework is going to take forever. This is so you understand what is going on. What we're actually going to do is not going to take nearly as long. In fact, by the end, we're going to be really fast at this. Like, I can look at this problem and tell you the answer right away. No, it's not 2. I'm not going to tell you. I don't want you to get the shortcut yet. But I'm telling you there is a shortcut, so I want you looking for the shortcut. I'm going to show you the way that we have to do this mathematically, but there's a shortcut coming. Okay? So be thinking about what the shortcut might be, but don't say it out loud until I ask for it, because I want everybody to think on it, think about it on their own. So if we have a problem like this, okay, we do not have a number over a variable. If we get a number over a variable, we can just say that equals 0, and we're good. That's our answer. So if we get something like limit as, if we get any of these that we had over here, we can just say 0. That's our answer. We go on. You'll see some like this on your homework. You'll put 0. You'll go on. All right. Now, I've got a fraction, and I've got x's in both places here. So what we're going to do for this is we want to divide each term by the highest degree variable from the denominator. Okay, so this is okay to do. The highest degree variable in my denominator here is x squared. So I'm going to divide this by x squared. 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 Okay? And then I'm going to simplify anything that I can simplify. So keep your limit notation. Don't be lazy, like I'm sometimes guilty of doing. 5 over x squared, will that reduce or simplify? It will not. So that's going to be 5 over x squared. Minus, what's x squared over x squared? 1. Okay. What about 3x squared over x squared? That's just 3. What about 9x over x squared? That's 9 over x. Okay, now I'm going to write this next step, but I normally would not. So I'm going to write it this time just so you see what's happening. So when we take limits, we can take the limit of the top of a fraction and the bottom of a fraction separately. We can also take the limit of things that are terms that are added and subtracted to each other separately. So what that looks like is I can actually just take the limit as x approaches infinity of 5 over x squared minus the limit as x approaches infinity of 1 over the limit as x approaches infinity of 3 plus the limit as x approaches infinity of 9 over x. So I don't usually write that step. I just do this in my head, but I want you to understand what's happening, so I'm writing it this time. I'm taking the limit of each piece separately because the properties of limits tell us that we can do that. What is the limit as x approaches infinity of 5 over x squared? That is 0. Because the bottom of that fraction is just going to get bigger and bigger and bigger. We're going to approach 0. So anytime you got, that's why we spent so much time talking about this, right? You got a number divided by a variable in the bottom. For big numbers, that's going to approach 0. What's the limit as x approaches infinity of 1? It's 1, because 1 is just 1. It's going to stay 1 no matter what. There's no variable there to change it, so it's just 1. So what's the limit as x approaches infinity of 3? Also 3. And what about the limit as x approaches infinity of 9 over x? 0. Okay? And so we get negative 1 on the top, 3 on the bottom, negative 1/3 is the answer. Everybody okay there? Let's try some more. All right. So, for example 10, I said to divide every term by the biggest degree variable from the denominator. What is that for this problem? X squared. It's not always x squared, but it is a lot of times. So we're dividing everything by x squared. Okay? So that means, if we simplify this a little bit, we're going to have 5 over x squared plus x over x squared. One of those x's will cancel, so we'll just get 1 over x there. We got 8 over x squared. And what's x squared over x squared? 1. Your last statement was incorrect there, Caleb. All right, so everybody okay here? Understand what's happening? All right, so 5 over x squared, number on top, variable on bottom. That bottom of the fraction is going to get bigger and bigger and bigger and bigger. That's going to be 0. 1 over x, same thing, right? Variable on bottom, we're going to get 0. What about 8 over x squared? Variable on bottom, 0. 1 is going to be 1 because it doesn't have a variable. So we get 0 over negative 1. And what is 0 over negative 1? 0. Not undefined. Okay, questions? All right, let's look at 11. What do I need to divide everything by here? Okay, x squared. Are we sure not x to the third? It's in the numerator, so we're not going to use x to the third. It needs to come from the denominator. So we're going to divide everything by x squared. Okay, so that will give us the limit as x approaches infinity of, what do I get when I do x to the third divided by x squared? X. Okay, 4x over x squared is 4 over x. One of those x's will cancel. 8x squared over x squared is just going to be 8. And then we got plus 2 over x squared. Okay, so this one's a little bit different, right? Because this part right here, I got this x, which is a little weird, right? Limit as x approaches infinity of x. What's that going to be? It's going to be infinity. Because you're just going to, that number Like if you're plugging in numbers that get larger and larger, you might plug in 1, then 2, then 10, then 1,000, then a million, then a gazillion. It just approaches infinity. What about the 4 over x? That is 0, number on top, variable on bottom. What about my 8 right here? That just stays 8. What about the 2 over the x squared? 0. So I've got infinity divided by 8. It is just infinity. There's not really much you can do to infinity to make it not infinity. Now you could, what about if I had a negative 8 on the bottom? Infinity divided by negative 8 would be negative infinity. It would change the sign, but it would still be infinite. Okay, questions? So you have to think about it a little bit whenever you get ones where you don't have a number or a fraction. The other ones we've looked at so far, you had these fractions where you knew it was 0. You have to think about it a little bit here. All right, 12. What should I divide by for 12? Okay, largest exponent in the denominator is just this x, so we divide everything by x. So that would give us the limit as x approaches infinity of x's will cancel here. We'll just have 4 minus 3 over x over 2 plus 1 over x. Okay. Limit as x approaches infinity of 4 is 4. Reagan, what do we get for the limit as x approaches infinity of that 3 over x? It's 0 because we have a number on top, variable on bottom. Here we'll get 2. Leah, what are we going to get for the limit as x approaches infinity of that 1 over x? 0. And so we just end up with 4 over 2, which is 2. Okay, here. All right. I want you to try the next 3 on your own. So try the next 3 on your own. Should get negative 1. Okay? 14 I'm going to actually do because there's debate on this one, right? This one's more confusing. You divide everything by x squared. So that gives you the limit as x approaches infinity of 4x minus 10x to the third over 15 over x squared plus 1. And what I saw a lot of you doing, you were good down here. You knew that was 0, that was 1. And then the top starts to give you trouble, right? Because you have numbers. So if you think about, I don't know if it's completely right to say you're plugging in infinity here because it's not really a number. But if you think of like plugging in really big numbers, right? You got 4 times infinity. There's 2 ways you can think about it, but there's one that's correct. So one way a lot of you were thinking about it was like 4 times infinity is infinity. And 10 times infinity to the third is also infinity. So infinity minus infinity is 0. But that is not the case. Because that infinity is to the third power. So if you think about those first ones that we were doing over here, what did we care about? The highest exponent. Because that, for really, really, really big numbers, that bigger exponent is going to overtake anything else, right? So, so when we look at this here, because this infinity is to the third power, it is the one that matters, right? That's the one actually, I should probably include that negative there. And negative 10 times an infinity is going to give you negative infinity there.
So going to 0 is like you're just like going halfway. I think going to infinity is like going all the way.
I'm not sure if I'm following you there. Or sure if we have time. All right. To chase that rabbit. Okay, and then for this one, you should get 0. Okay, you guys need all right, so, shortcuts. Anybody figured out what they are?
Just turn them into 0 if it's the big exponents and the actual number. Right?
Okay, I'm going to give you a shortcut. So, like, I do all of these without ever dividing or anything like that. There's a phrase that I use for a shortcut here. It's crazy, but it works. This is one of those examples. Coach Wood taught it to you, didn't he? For horizontal asymptotes?
Oh, yeah.
Bobo Botno eats DC.
He was talking about watching DC or something.
Yeah, so he did this for horizontal asymptotes, which at the very beginning of this, we talked about these are going to be your horizontal asymptotes if you're looking at the graph, right? So, bigger on bottom, this O right here is a 0. So if you have a bigger exponent on the bottom, then that limit's going to go to 0. If you have bigger on top, not 1, so that means there's not a horizontal asymptote, which means it's either going to go to positive or negative infinity. So you might want to put that over there, positive or negative infinity. And then exponents are the same, divide coefficients. All right, I want to show you this on your homework to show you how quickly this can work, okay? Let me pass this out so you're looking at this. I think they just said they had extra.
I saw you.
You guys have an extra? I don't even. Okay, let's look at this real quick together. All right. So let me show you up here how quickly this can work. Okay. So really, remember I said like only the biggest exponents kind of matter, right? Because whenever you divide by that exponent, if you have a fraction, a 0 in the bottom, it just doesn't matter. So here, my exponents on top and bottom are the same. So I'm just going to look at the coefficients in front of, you only look at the, so I would only look at the ones that have the bigger exponents, right? And then I just, since they're the same, exponents are the same, that's your eats DC, divide coefficients, 1/2 is the answer to that. What's the answer for number 8? It is 0, because your exponents on the bottom have high, and you don't have any exponents on top. You have a higher one on the bottom. Okay, ones like number 2 are a little bit tougher. You may need to actually do what I showed you on those problems here. What am I going to get here?
Get x plus 4 over 1.
Yes. So I could go ahead and divide here, but this one's bigger on top, so that tells me I'm going to get positive or negative infinity, right? There's not going to be a horizontal asymptote. So these you may want to actually go through and divide here. So you got x plus 4 over 1 minus 2 over x. So you end up with like infinity plus 4 over 1 minus 0. So that's going to be infinity over 1, which is just infinity right there. You have to think about that a little bit. It really comes down to, if it's bigger on top, you're looking at that biggest exponent for whatever is on top. If I was approaching negative infinity here, actually, it'd still be positive for this one because it's squared, but like if that was third power, it could be negative infinity. Number 9 is like those first problems that we were doing. It's not a fraction, so it's going to be positive or negative infinity. You really only care about that biggest exponent. Yep, so it would be positive infinity. Yeah. So, do you guys see what's through here? Now, 21 through 27. These are some challenge problems. They have some stuff about them that we haven't looked at algebraically and we're not going to. You can use a calculator or Desmos if you don't have a calculator at home. For that,